Colloids. Colloid or a colloidal dispersion is kind of like a solution, but it's different. So colloidal particles are small enough that they will stay suspended, but they're larger than typical solute molecules. So if you ever had hot chocolate or chocolate milk, and if you leave it for a little bit and you come back, you need to stir it, right? Because the chocolate settles out to the bottom. The chocolate particles are too large to stay in solution. So that's not a colloidal suspension. Those are going to settle out. But if you have milk without the chocolate in there, is that going to settle out? Not if it's homogenized. If it's raw milk, it'll separate into things. But homogenation makes the particles small enough that they stay in suspension. So milk is an example of a colloid. Colloid particles are typically 1 nanometer to 1,000 nanometers in diameter, so they are much, much larger than individual atoms in molecules. Some colloidal particles are visible under a microscope, and we watched this video before, and we're short on time, so we're not going to watch it again. But you can see the particles jiggling, right? And that's because they're being hit by water molecules. That's called Brownian motion. Soap can form micelles, which act as colloidal particles. So we learned about soap earlier as well. Here's a soap molecule, long nonpolar tail with an ionic head. You get a bunch of these together in water. These nonpolar tails don't like the water, right? Because the water's very polar. And so the nonpolar tails are going to all huddle together and stick the ionic heads outside where the water is. And so this will make a micelle of soap. So a lot of times a soapy solution is going to be slightly cloudy because these micelles and all colloidal particles are large enough to interact with light. And so they will deflect or refract the light. These little particles are going to be stable instead of just separating into a layer like oil would, because when they make these little micelles, now they're surrounded by these negative polar heads, and the negative heads on the one micelle don't like the negative heads on the other micelle, and so they stay separate little pieces. And then these can essentially swallow up grease or fats, oils, will dissolve in here and then can be washed away. Proteins also form colloids. Those are called macromolecules. They're really big. Here are examples of colloidal dispersions. You have different combinations of phases. Thanksgiving's coming up next week. Whipped cream. That's a colloid. It's a suspension of gas, air bubbles, in butterfat. That's my favorite. You have to put some pie under it, though. The Tyndall effect. Here we have a beam of light going through two liquids, right? In the first liquid, you can see where the beam of light is going, and in the second liquid, you can't. The second liquid is a solution. These particles are too small to interact with light, and so the light just goes through and you see no effect. This is a suspension where the particles, a colloid, this is where the particles are large enough that they can interact with the light, to scatter the light. Another place you'll see this is sunbeams. So, the sun's streaming in your window, and, oh, look at the sunbeams. Yeah, you need to dust your house, right? Don't look at my house. There's way too much dust in the valley. But how can you see a sunbeam? It's because there's little dust particles in the air. They're suspended in the air, right? It's a colloidal dispersion of solid dust particles in the air. And as the sunlight hits it, it gets scattered and then we can see it.